This deeper understanding of the atomic structure primes us for a grasp of the molecular structure, which together with atomic structure forms the intrinsic material properties. These structures, partnered with factors like temperature and energy states, weave the physical and chemical tale of a material. The story of a material property does not stop at individual atoms. It extends to how these atoms arrange themselves in a repeating pattern, forming what's called a crystal lattice. This spatial arrangement of atoms or molecules, chronicled into a three-dimensionally repeating pattern, is what we refer to as the molecular or crystal structure of a material. The lattice points in this array could signify a single atom, a group of atoms, or an identical molecule, all depending on the material type. What's interesting is that different properties are exhibited by different materials, not only due to the type of atoms participating, but more importantly, due to how they are ordered in the crystal lattice. Graphite and diamond, both fellow carbon atom assemblies, despite their similar atomic composition, sport vastly differing properties due to their distinct crystal structures. One metal of particular interest in this context is copper, which boasts an efficient crystal structure. This face-centered cubic structure, or FCC, means that every copper atom inside this lattice is neighbored by 12 other copper atoms. This manner of atom packing is highly efficient, creating a uniformly conductive matrix traversable by cushioning free electrons. Bend or twist a wire of copper and it still maintains its electrical conductivity. This is because the FCC lattice, organized and compact, enables the outermost electrons to wander equitable throughout the lattice structure, making conductivity possible. Understanding the molecular structure paves the way for uncovering the role of temperature and energy states in a material's properties. Together, atom structure and the molecular structure and configuration are the building blocks of the material universe, shaping our understanding and application of these materials in myriad ways. The atomic and molecular structures lay the groundwork to understand a material. But there's an eminent external factor that meets these intrinsic material properties and influences them: the temperature. Temperature, in simplistic terms, is a measure of heat energy. This heat energy, provided from external sources, impacts both atomic as well as molecular structures, and hence is significant in modifying the behaviors and functions of materials. At the atomic level, the dynamics get interesting. Temperature boosts the kinetic energy of atoms and molecules, inducing and intensifying their vibrations. As we turn up the heat, the vibrations become more vigorous, a kinetic upheaval disrupting the sea of free electrons. In metals, disturbance in the sea of free electrons, the very essence of electrical current, increases electrical resistance and reduces conductivity. At the level of crystal structure, temperature plays its part by influencing phase changes, transitions of a substance from one state of matter to another. A solid can melt into a liquid, and a liquid can vaporize into a gas as heat multiplies. During phase change, as the crystal lattice unravels, this transforms material properties. From strength to hardness to transparency to conductivity, all are changed. The story of copper as an excellent electrical conductor can't be completed without considering the role of temperature. While its atomic and molecular structures attribute to its excellent conductivity, the application of sufficient heat energy can overpower its internal bonds. Temperature emerges as a pivotal player, influencing atomic movements, molecular alignments, and energy states, steering material properties in new directions. Heat from environment or current can cause the metal to melt, severing a connection. This temperature-induced transformation, not unique to copper, underlies the principle of a fuse. Within these phase transitions, within the intricate tapestry of atomic and molecular structures, electron movements and energy states become mere variables for the engineer or hobbyist. We witness a manifestation of the Dharma, reflecting the interconnectedness and harmonious influence of three elements that contribute to and are shaped by each other. No single negation or relationship between two variables can ever explain a triad fully. Only by identifying and understanding the three factors involved do we comprehend. In the triad bind an atomic and molecular structure with kinetic energy, we also draw analogy to bhakti, devotional love, in the logic of inclusion. Here, the atomic structure defines the possible molecular structures which, along with the atomic structure, respond to temperature by establishing conductivity, among other attributes. This relationship reflects devotion and surrender. where all individuals contribute to and are affected by their greater purpose. Devotional love for a greater cause guides the individual in aligning their actions conducive to a goal. Atoms and molecules are guided by the heat of the material to transformations in structure. As in all things, three components must be considered together to understand. Thus defines a basic triad of the universe's fundamental logic, and bringing us all one step closer to God. Amen.